So we have Terrance who's going to be talking about confidence ranked reconstruction of census microdata from published statistics. Thanks, Terrance.
Okay, yeah, so today I'll be talking about this project where we're trying to reconstruct data based on like published statistics. And this work was done in collaboration with my co-authors listed here. So real quick, I'll just kind of sketch out what this problem looks like. So essentially you have some private data set, and the entity who possesses this private data set wants to release some information about it. But they don't want to actually release like the full data set itself. So often this comes in the form of releasing tables or statistics. And so in reconstruction attacks, the basic idea is that you want to design algorithms such that it takes in as input these statistics and then is able to reconstruct some of the rows in the original data set. So for example, some of you might have heard like the US Census has run like its own like internal reconstruction attack on the decennial census. And what essentially looks like is this. So they set up this integer programming problem and they set up each statistic as a constraint. And then what they report is that if you run their reconstruction attack on every block in the United States, you get a match rate of like roughly 46%. So there's a lot of ways you can do reconstruction. And like the version that we were sort of interested in is this idea that we call ranked reconstruction. So the idea is just this. So given a set of published statistics, you want to output a list just like before of like candidates. But the difference is that not only do you want to output this list, but you want it to be ordered in some way in terms of confidence. So like ideally, items at the top of the list are more likely to actually be true matches versus items at the bottom. So I don't have too much time to really talk about how the algorithm works, but I'll kind of sketch it out like very briefly or talk about sort of the motivation behind it. So there's this line of like related work within differential privacy called like query release. And people have essentially designed algorithms that use synthetic data to sort of like improve performance. And the idea basically is that like you want to release like statistics with privacy. And one thing you can do is essentially fit some type of synthetic data generation algorithm to these statistics. And the goal is that like when you output this synthetic data set, the calculated statistics, like these synthetic answers are like pretty close to the original ones. If you look at this diagram here, this problem like synthetic data generation and data reconstruction are like very similar. They're like nearly identical. And so like thinking about this a little bit more, we realized that like, oh, maybe we can leverage some of these like modeling advancements from this one like line of research into data reconstruction. So there's like a lot of like recent algorithms for synthetic data generation that we could have picked from, but we just decided on this one called wrap or relaxed projection. So roughly speaking, the overall like method is somewhat simple. We essentially take the set of statistics and repeatedly fit this like model or this like algorithm relaxed projection to this set of statistics. And basically for each run, we generate as many like samples as feasibly possible. And then we just rank these samples based on how like frequently they appear across all these different runs. Empirically, we showed that essentially the more runs you do, the better performance you get up until maybe like 40 or 50 runs, at least like for our data sets. Okay, so now I'll just jump into the empirical results. So for this talk, I'll only be talking about the decennial census. But in our paper, we also try reconstructing like higher dimensional data in the form of ACS data. And in that case, there's like both more columns and also the statistics or there's like a higher number of statistics too. So real quick, so what metric do we use to evaluate these results? So we just created one that we call metric K. So what this essentially says is that given some lists of, or some ranked lists, what proportion of the top K candidates in my list are actually true matches? So essentially you'll see like plots like this. And assuming that you do have a list that's like ordered in terms of confidence, you'll see that at the top of the list, when K is small, you should have a very high reconstruction rate. And as you go down the list, it should start getting worse. And real quick, in case like you guys like see it and see this little like strange, we essentially normalize the x-axis to be between 0 and 1. This allows us to sort of average results across like many different data sets of different sizes. Okay, so what data do we use? As I sort of alluded to before, so the US Census Bureau collects data every 10 years in the form of the decennial census. But instead of actually releasing the raw records, it releases the set of tables. So we don't actually have access to like true like census data. But what the Census Bureau did do was a couple years ago, they released a synthetic file for researchers to sort of experiment with. And taking a look at this data, essentially the US Census like breaks up the country into these geographic entities. So you start with the country's broken down to states to counties, counties into tracts, and tracts into blocks. And so we tried attacking like random data sets both from the block level and the tract level, like selected from all 50 states. Real quick, there's like basically 4 columns that I get that are collected by the Census Bureau. In addition, for like tract level reconstruction, there's this additional column where we have to basically reconstruct what block a person lives on. And as far as like what statistics we use, we basically just follow what the census did in their own internal reconstruction attack. So we picked like these tables here. And they're just basically like different counts across like different attributes, like how many people are of this race or this age on every block. In total, this amounts to 600 queries for or 600 statistics for every block. And for tracts, it goes anywhere from 10 to 50,000. That just depends on how many blocks are in that tract. So I'll kind of break up our results, at least over this experiment, to like different stages. So the first thing is just like you want to look at what the actual results for our method looks like. Especially just paying attention to like the shape itself. And the fact that it's like decreasing with respect to K means that this whole idea of being able to do like rank reconstruction is like feasible, at least for our method. So it's not something that like doesn't really make sense. And so now the question is like, okay, like what do these numbers actually mean? Like, is there a way to somehow like contextualize it? In general, like this is something that I'm starting to think a little bit more about because it's still unclear exactly how to make sense of like what these numbers mean. Like obviously you want something really high, like close to like 100% reconstruction. But once you get it down lower, like what does it mean that like at K equals 0.8, you have like 0.7 like reconstruction? So this is something we're still trying to figure out. But at the time of publishing this paper, we decided to construct a set of baselines sort of based on this idea of like prior information. So for example, if you knew nothing about the private data set, your prior would essentially be uniform, right? You would essentially be randomly guessing and creating a rank list based off of this. So of course that wouldn't work really well. So the idea that we were trying to think of is like what's more realistic in this setting or in the real world. And what we did essentially was create like a hierarchy of like data sets based on the same like geographic entities that the census uses. So for example, like suppose I want to reconstruct a block. And I don't know what that block looks like, but maybe I know just based off of like public information, like public records, what the city looks like or what the tract looks like or what the county looks like. So suppose I had access to this information. What does reconstruction look like? How many rows can I then reconstruct? And then the question is like, okay, how much more can that information do I gain when I have these like statistics that are released by the census? So concretely what this looks like, so for example, let's suppose you want to simulate the idea of having access to the state distribution. I just go to the census data, look at all the rows in the state data, and then just rank them based on the frequency that they appear. And sort of like as expected, like as you go up the hierarchy, the results get worse and worse. So for block level reconstruction, if you use tract level data, which is like fairly close to a block, you do like okay, like reasonably well, and like very quickly the results get worse and worse. And the main takeaway is sort of just that like, yes, like this information is public, and it is like maybe somewhat informative, but you gain a lot more information or you leak a lot more information just from the statistics from the census. Okay, and then lastly, there was another experiment that we wanted to do, was essentially kind of build this like unrealistic scenario. So for example, you had a private distribution. You don't know anything about it, but perhaps there exists some public distribution that's very close to this private one. So obviously in like real world scenarios, this probably doesn't exist, but we want to see what happens in this case. So to do this, we simply split up the data set into a private and public data set. We call this public information just like a D holdout, so a holdout set. So then the same thing as before, we just reweight or re-rank the items in the holdout data set. Essentially, this is what it looks like. So like kind of by design, we made it such that the holdout set, or just splitting things out, we get a holdout set that's like very close to the private data set. So as you can see from the pink line, your reconstruction rates are like extremely high, like 90% even for like the lowest value, okay? So obviously like this prior like knowledge is like very strong. It's like much better than what you can get from just the census statistics. So the question is like, okay, given this scenario, like sure it doesn't actually happen, but let's say we're in this like setting, like is there any like danger in releasing these census statistics then, or is everything like kind of free game? And so we pretty much like took a very naive approach to it, and essentially you can take this relaxed projection method and just initialize it to this holdout set. So it's almost like pre-training fine-tuning, or it's like combining both like the holdout set information and like statistics information. And otherwise, like the algorithm runs the same. And as you can see here, now you have our reconstruction tech still does better than this like extremely strong prior. So there's really like, I think there's two takeaways from this. Like first of all, it's just saying that even in this scenario, whether you have a lot of information about the prior distribution, these census queries still leak additional information. Like it still puts additional people at risk. And I think more importantly, like if you think about reconstruction text more broadly, if you do have like prior knowledge or public information about some like data set, yes, it makes sense to use it that as a baseline, but you should also kind of think about, can you incorporate that into your reconstruction attack? Because chances are you can probably improve your reconstruction rates. Okay, and that's that. Okay. The question. Oh, sorry. The question is just if we add like DP noise to these statistics, what happens? So we actually haven't done this yet. But this is something I'm like currently doing this semester. So hopefully we'll have more results on this soon.
About like how much the rankings are affected by maybe like the density of the kind of data in distribution. So for example, like if like white is more common than would the ones that is white maybe tend to have higher rankings,
Right.
Because it's sort of older
I think it's so that does happen. I think it's more by design the algorithm, right? So let's say you have a bunch of white males in the data set. So naturally a synthetic data generation algorithm trying to match that original one would have to output many white males, for example. So then obviously if you just count the number of white males in like the final like set of like things, it's going to be really high. So it's kind of by design, like things that probably appear more in the private data set will be higher on the list. We're thinking about like other variations of this attack, and there's like slight like changes you can make to like, it kind of just depends on what your like evaluation metric is. But for yes, for this setting, that is sort of what happens.